Hi there, my name is Yak Xuan Ching, and today I'm going to present about the topic Probability of Failure Prediction of an Offshore Platform using Python. Offshore platforms are one of the biggest structures that we can build with our current technology. Each offshore platform carries all the equipment needed for operations such as extraction and storage of oil and gas from the field. These offshore platforms, however, are built to withstand the harsh conditions that most man-made structures fail to withstand. The reliability of these platforms are being put to the test during the operation of extracting oil and gas from the reservoir. Although these platforms are being designed to have a lifespan that covers the entire estimated time required to extract all oil and gas from the reservoir, the platforms may need to extend their lifetime when there is still oil and gas remaining to be extracted. Before this can be done, the reliability of the structure needs to be assessed. There are various methods being used by structural engineers in analyzing the reliability of the structure. Reliability can be understood as the chances for something not to fail. So to find the reliability of the structure, they find its complement, the probability of failure. Most structural engineers simulate various loads acting on a structure and use the data acquired from the simulation to calculate the probability of failure of the structure. Simulation-based and statistical software are being used for this purpose. In the fourth industrial revolution, the application of data science has become a trend that all industries intend to follow. Data science is a field in which a phenomenon can be described with data that has a specific pattern. The analysis can be done by artificial intelligence, or AI for short, which is another feature that most industries are aiming for. So, the questions of the day. Is it possible to conduct structural reliability assessment of fixed offshore platforms using data science tools such as Python? So, the objectives of this research are to investigate the feasibility of data science application in the oil and gas industry for life extension of offshore platforms, to compare and study the type of algorithm or software used for statistical analysis in life extension of offshore platforms, and to calculate the probability of failure of fixed offshore platforms based on the simulation data from pushover analysis using Python. As for the scope of this research, the design of the Python algorithm that will be used to perform structural reliability assessment with the data from the pushover analysis will focus on. This includes the documentation for Python libraries such as NumPy and Matplotlib. The stress-strain interference method has been studied as well to find out the necessary steps to determine the reliability of the offshore platforms. So, in this research, I created a Python algorithm, a rather simple one, as the beginning of the development of the algorithm for machine learning. This algorithm includes the functions to read data from a Microsoft Excel workbook, which I call it as an input file. You can see from the name I gave to the file. The input file consists of data output from a pushover analysis done by the industry. Pushover analysis can be understood as an analysis where the simulated load tries to push the structure until the structure collapses. Here, the loads simulated are the environmental loads, mainly waves and sea current. These loads can be simplified as a resultant horizontal load applying across the base of the platform, which is known as base shear. The strength is, well, the ultimate strength of the platform. The simulation gives the data for base shear and reserve strength ratio, or RSR, for 100 years. The ultimate strength can be calculated by multiplying RSR with base shear. Apart from this data, the file also included the probability for base shear and ultimate strength with respect to each of the values. These probabilities were calculated using a statistical software named Minitab by the industry who provided the data. This is how the content of the file looks like. The table here has the 4 columns, which are the RSR for 100 years, the base shear, the probability for base shear, and the probability for ultimate strength. As the platform is a monopod as shown here, the simulation has been done for 12 directions. You can see from the list of worksheets here, so that's a massive amount of data to deal with. The next process of the algorithm starts here. To find the probability of failure, the product of the two columns, which are probability of base shear and ultimate strength, needs to be calculated. This is the part where the stress-strain interference method is applied. Basically, the selection of equations to be used can be done with the numpy where function, which is similar to the if function in Microsoft Excel. The integration can be treated as the sum of the values, so the numpy sum function is used. Once the probability of failure is calculated, the next step is to calculate the return period, which equals to 1 over the probability of failure. Return period is like the probability, but in the expression of how many years before one failure will happen. Now, to store the results calculated together with the whole data table in another file, I added these few lines for Python to open a file with names that indicate the direction of waves, and write all the results into that file. Note that these processes are only for one of the 12 directions. So from the line that tells Python to read data until this line that tells Python to write the result into a file, all of these were repeated for another 11 times using the for loop. The last part of the Python algorithm is to plot the radar chart for the probability of failure calculated, together with the target reliability as specified in ISO 19902. This part of the Python algorithm is based on an example from the matplotlib documentation website, as there are no Python libraries that can plot radar charts with a few lines of code. So this is what the radar chart looks like. That's all for the Python algorithm I created. Now, these are the results computed using the Python algorithm I created, and these are the results computed using Microsoft Excel with the same method, which is stress-strain interference method. This shows that the Python algorithm is capable of computing the results with high accuracy if we compare it with the results from Microsoft Excel computed with the exact same method, which is stress-strain interference method. However, when we compare the result computed using stress-strain interference method with the result calculated by the industry using another method called Global Ultimate Strength Assessment, or GUSA, that's what they call it, we can see that the result differs from each other. Here's the percentage difference between the probability of failure calculated using stress-strain interference method and GUSA. Based on the table shown here, you can see that some of the results have huge differences compared to others, as much as 14.9 billion% for the waves coming from 34 degrees, while the lowest is around 23.22% for waves coming from 64 degrees. The negative sign indicates that the results computed using stress-strain interference method is less than the result calculated using GUSA. The difference is because for stress-strain interference method, the probability of failure depends on the conditions. Either the probability of base shear is larger than the probability of ultimate strength, or vice versa. However, for GUSA, the value is calculated through the two equations here, which eliminates the possibility of misinterpretation of data. Another possible cause is that for stress-strain interference method, the probability distribution for both the base shear and the ultimate strength depends on which probability distribution is the best fit for each of the data, which can be reflected in the use of Anderson-Darling test, one of the goodness of fit tests used in statistics. For GUSA, on the other hand, assumes that all data follows log normal distribution. Now, we compare the result calculated using both methods with the standard. The standard for the reliability of offshore platforms used in the industry is ISO 19902, which specifies the target reliability of the offshore platforms based on the combination of consequence category and life safety category, as shown in this table. From the information provided by the industry, the fixed offshore platform in question is categorized as L2 category, which the target reliability needs to be less than 0.0005. Here is the radar chart or spider chart that has the probability of failure calculated using both stress-strain interference method and GUSA, as well as the target reliability specified in ISO 19902 for L2 category. From this chart here, we can see that none of the values exceeded the target reliability as specified in the standard. So, we can conclude that the offshore platform meets the minimum requirement in structural reliability as specified in ISO 19902. At the end of this research, I would like to conclude that although structural reliability assessment is still being done manually with the use of various software for the time being, either the statistical software developed with functions accessible with a few clicks, or softwares that are capable of performing mathematical evaluation with command line style input, it is possible to utilize data science application in this assessment, as well as for other engineering analysis in the future. For the structural reliability assessment on the test structure using Python, it can be concluded that the result is acceptable with reference to the standard. However, I recommend further research on this topic as the current research only uses simulation data for one platform. The performance of the Python algorithm shall be tested with simulation data from different types of platform. Thank you for watching.